All right, hello everyone. My name is Scott Levy. I'm a PhD student at University College Dublin in Ireland, and welcome to my talk on accelerated, segregated, finite volume solid mechanics solvers using machine learning. So the overall aim is my work is to use machine learning to speed up open form solvers. So what do I mean by speed up? Okay. By speed up, I mean a method that produces the same result in a shorter total time. And ideally, this method could be applied to an unseen case. So you would give me an unseen case, I could apply my method, and I would get the same results in a shorter amount of time. So the approach I've developed then for a specific test case is to run a coarse mesh version of the test case, train a machine learning model to predict the converged solution, and use this machine learning model to predict the solution for a fine mesh test case. So the overall hypothesis is that the computational time required to do this will be less than running the fine mesh case conventionally in OpenFOAM. So for solid mechanics then, the governing equation is a conservation of linear momentum as shown here. For small strain problems, which is what I looked at initially, this is the constitutive law. So subbing these in, this is the final momentum equation, and I'm using solids for foam. So in solids for foam, this is solved using a segregated solution or procedure, and it's split up implicitly and explicitly the terms as shown on screen. So this equation is solved using a linear system as shown. So in a segregated solver, this linear system is solved separately for each direction. So each source term is a function of the displacement solutions from the previous iteration. So once this is solved, this produces a new displacement field shown by ux, uy, uz, and then this is used to form the new source term in the next iteration, and so on, so on, so on, until we reach convergence, which is where the residual is below a certain value. So part of my motivation was to wonder what does this pattern look like? So what do the unconverged displacement fields look like until they converge? So to figure this out, I took a simple 2D test case, picked a cell in the center, and I plotted the displacement over iteration. So this is the start of the iterative process, and this is the converged solution. So then I also wondered, is this similar for a fine mesh test case? So I picked a cell in a similar location and did the same thing. And as you would expect, they're quite similar. So then I asked the question, can a machine learning model trained on the coarse mesh data predict the fine mesh patterns? So to look into this more, I did the same thing, except for this region in the lower right corner of the same test case, and plotted the results. So from this, what I took that the coarse mesh data, i.e. the blue lines, are very, very similar to the fine mesh data. So if I could train a machine learning model to predict the solution of or trained on just the blue line data, I could predict the orange line data, i.e. the fine mesh. So what would this machine learning model look like? Well, I thought that it would be good to use how this sequence of patterns progresses to train the machine learning model. So I would use the initial iterations as inputs and the final iteration as the output, as you can see here. So how the data set will be set up then, each data point will be for each cell in the mesh, and the input features will be the displacement for each direction for each training iterations, and you would choose n training iterations to train the machine learning model, and the output is the converged solution. So to go run through the solution procedure, the first step is to run the full case of a coarse mesh and store the training iterations and the final iterations. So I used n is equal to 20. And then this is what the data set looks like for, as I showed previously. Yeah, except I've selected 20 and the converged solution here. So then the model I trained is an artificial neural network using Keras and TensorFlow. which has multiple hidden layers, and it's trained to a target loss of with a loss function of mean squared error. So yeah, so third point is to run the fine mesh case. So this blue line now is how the case converges using OpenFOAM conventionally. So this is without any machine learning speed up. So I'm comparing it to this. So the orange line is the first 20 iterations. So the fine mesh case iterates conventionally, and these displacement fields are stored. Then I make the prediction. Once the prediction is made, however, I can't calculate directly the displacement values at the traction boundaries, because as I showed previously, the sigma fields and the grad d fields are explicit. So I perform this loop to calculate the displacements on the traction boundary. So after the prediction is made, I allow the case to come to convergence. And this is what it looks like. So it doesn't look like great results. Maybe it reduces the total number of iterations slightly, but overall it doesn't seem like it's good. However, when we look at this closely, instead of looking at how many iterations it requires, I look at the total computational time this requires. And as you can see, there is a big drop in the residual convergence. So just to explain this graph more, this change in time here is the time required to run the coarse mesh case and train the machine learning model. So it's relatively low. And then this spike here, this is between iteration 20 and 21, and this is the time taken to run that boundary correction. So for this case, if you were to run it to a tolerance of 1 e to the power of -8, you would get about 2 times the speed up. So why is this faster? To answer this question, I looked at the number of linear solver iterations. So the relative tolerance for the linear solver will stay the same. So for the conventional method, this stayed at around 500 iterations to reduce the relative, to reduce the tolerance of, to solve the linear solver. And when the machine learning model makes its prediction, the number of linear solver iterations required drops dramatically. So some qualitative results then. This is the displacement error field. So this is the difference between the underconverged displacement fields and the converged displacement fields. So on the left, with no machine learning, you can see this is relatively high. And then compared to where the machine learning model makes the prediction, this is qualitatively lower or darker. To compare this then even more, I've warped the vectors in the z direction. So the higher in the z direction, the greater the error. So you can see that the no machine learning case is predominantly higher than the machine learning prediction. So then a reasonable suggestion would be that if I had the coarse mesh solution, why not just linear interpolate this to the fine mesh and use this as my starting point? So I tried this. And this does work better than the conventional case, but not as well as the machine learning case. So if you were to compare it to this method, it's about a 1.4 speed up. So moving on to different test cases then, I moved on to the 2D cantilever beam case. So this case is notoriously slow for segregated solvers due to the aspect of its geometry, or the aspect ratio of the geometry. So yeah, as you can see here, the machine learning prediction, which is the orange line, decreases a lot faster than the conventional solution, and in comparison to the linear interpolated method. So this resulted in a speed up of about 13 compared to the conventional method. So then for a 3D test case, this is a 3D elliptical plate. Again, the machine learning method outperforms the conventional and the initialized approach. However, the machine learning method is quite similar to the initialized approach for one prediction. However, one thought I had was that once the residuals return to a steady convergence rate, why not make a second prediction? So use the exact same methodology, except train a separate machine learning model at a lower residual and use this to make a second prediction. So that's what I did, and as you can see, this increased the speed up a fair bit. So the speed up versus the conventional for this case with 2 is now 2.85. So the machine learning training was slightly longer because I had to train 2 models. However, the speed up was greater. I applied the same then to a 3D narrative member case as shown, and this resulted in speed ups of just about 2 as well. So then I moved on to nonlinear geometry or large strain problems. So the governing equation and constitutive law changed. So the governing equation allows for deformation, and I use a Neo-Hookean solid. So the first test case that I tried was a static 3D cantilever beam. So this case takes very long to converge. So you're talking about 120,000 seconds. So I think that's, I don't know, like maybe 40 hours, something like that. So so the first prediction isn't amazing, but after the second prediction, this is when the speed up is really achieved. So after I ran this, instead of making the prediction at a set residual, I made the prediction when the residual started to return to a steady rate, and then this resulted in more speed up. So for this case, running this method was 25 times faster, and if you ran it against the initial case, I think it was 17. So I also apply this methodology to case with multiple time steps, so not just one time step. So the way the machine learning model is set up, I can train one machine learning model on multiple time steps of information and use that machine learning model to predict at each time step. So looking at the results here, you can see that the machine learning model converged much quicker than the fine mesh cases. So again, I'll just looking at the error for this case, I just want you to see that the error in the machine learning prediction on the right is lower than on the left, but as the time progresses, the error increases. So a reasonable explanation for this is that as the time step progresses, the difference between the fine mesh and the coarse mesh solution, the error compounds. So this is in line with this graph now, which is showing the speed up of each time step in comparison to the time step. So it's greater at the start, and as the time steps continue, the speed up drops off just because of the compounded error that I just mentioned. So some limitations then to this approach. This requires a coarse mesh, which may not be possible. So if you have a complex geometry and you can't make a coarse mesh out of it, then this obviously won't be applicable. You also have to select these parameters relatively carefully. So here I'm comparing the speed up when I vary the training loss and the number of training iterations. So you can see on the left that the speed up is clearly a function of the training loss. So this is because if you train the machine learning model loosely, this is quicker to train, so the speed up will be better. However, the prediction may not be as strong, and vice versa. If you train it to very tight tolerance, this is going to affect the overall speed up. Same for training iterations. If you use 2 training iterations, you have much less data to train on, so it's much faster to train. However, the prediction might not be as good. So and then another limitation is that this I ran about 10 different cases this worked for, but this case it doesn't work. It's a cylindrical pressure vessel. So I guess the prediction makes it worse. I suppose this might be because the residuals converge very quickly. I haven't come to a full conclusion on this, but I just included this to show that I guess like some solvers diverge. This doesn't work for every case. But I guess this is part of my future work as well. I want to implement this into simple foam or into fluid mechanics. So this is a naive implementation where I've applied the exact same methodology basically for just predicting velocities, and the speed up is quite low, so it's 1.16. So I would hope to maybe including pressure in my input features, and maybe predicting pressure over velocity might affect this. But this is part of the ongoing and future work. So that concludes my talk. Thanks very much.
Okay, thank you very much. We have an online question, so maybe you can answer first. So in terms of advantages of the machine learning acceleration on finer meshes, does the advantage still hold when accounting for the time required to obtain data and the machine learning model?
Yeah. That's what might take a while to go back here, but yeah. So in any of the graphs, I've had computational time on the x-axis, the starting point for the convergence. So where the machine learning model starts here, I don't know if you'll be able to see this online, but the difference between where the conventional method and the machine learning method starts is the time required to run the coarse mesh and train the machine learning model. I point this out in an earlier slide. I'll try and find, yeah, there. So it's pretty small here.
Okay.
Yeah.
Okay, thank you. Do we have other questions? Okay, I do have that. So for transient problems, will there be issues of error accumulation? Because in this case, if I understand it correctly, the input of the next prediction will be the output of the last prediction. Am I right? For transient problem?
No. What? I don't quite.
So let's say we use the solver to solve. We use this solver to solve a transient problem, and couple with this machine learning model.
Yeah.
So during the iteration process, over time, you need to make predictions continuously with time.
Yeah. So for each time step here, there's a prediction being made. So a prediction is being made, and then it's converging.
Okay.
So it's converging to the same residual as this conventional case. And the point I was making is that the coarse mesh, because the coarse mesh solution will compound an error in training. That's why the speed up is better at the earlier iterations, because here the machine learning model is going to have to extrapolate more. Does that answer your question?
Okay, I think I understand your answer. Okay, thank you. Thank you very much.